what I was asking for. I can take a look at and manually do that. On the other hand, if we replace it with the successor, so if we wanted 41 to go up here, how do I actually replace it with 41? What happens if 41 has a child like 37? What do we think would happen there? Yeah, so what we do is we'd kind of connect this. So when we replace it with the predecessor successor, we're essentially saying remove this from the tree. So the same rules would apply where if when we remove this node, if it's got one child, we just connect its parent with that child. If it's a leaf node, we can just remove it. So its parent no longer links to it. So we'd get this, which I guess is kind of really just doing which is kind of just putting 37 up here, which we still see as ordered because now, again, from 41, we go left and right to 37. So that's great. So we've still maintained the binary search tree property. Now we need to think about, is this tree ordered? So again, although the difference is here, there is a difference there. The heights of 37 and 19 are still within 1. Again, this height is 0, this height is 1. And again, still over here, we've got 0, 1. So this is 2, 2. And so we see that everything's still balanced in this tree. So if we replace it with the predecessor, it does result in a balanced tree. I talked a little bit about this in the video where in this, I think, well, actually in the video, I think it was the opposite case where it's not like always replacing with the predecessor or the successor is a better choice. It kind of depends on the structure of the tree and what the order that you insert and remove different elements. And we'll get more practice with that, adding and removal today with the worksheet. Any questions about this? It seemed like most people got this, and I can take a look if there was an issue with actually just writing the predecessor or spelling or something like that, because it would only look for the very specific thing. Actually, I think I have the thing up here already. So last day, what we did was, I believe we finished the whole first page where we kind of talked about the binary search tree properties. We actually talked about the code for a rotate and one of the double rotates. And then we talked about kind of the 4 different cases that we see here, which is the same as the 4 that I outlined in the video, which it's when there's a left-left imbalance, a left-right imbalance, a right-right imbalance, and a right-left imbalance. But instead of kind of going over these again, I think we'll just move to the second page because we'll see probably all 4 of those different imbalances as we work through different examples and do a bunch of insertions and then removals. So again, this one example just, again, kind of gets us to not even have to think about anything beyond the nodes that are involved in the rotation, and anything below those nodes, all the subtrees below those nodes are just going to always kind of stay in between their 2 parent nodes, because that's how the binary search tree property works. We know anything in a subtree, in T2 here, for example, is going to be greater than this and less than this. Anything in T3 is going to be greater than this and less than this. So again, we know that all the values within these different subtrees, they fall in a range based on their parents. Again, T1 is obviously lower than this, and T4 is greater than all these nodes. And again, how we maintain that property is just, again, by that kind of adoption of passing a subtree off to another one, so it still stays in between those 2 parent nodes. So what I'll say here, if an insertion occurs in subtrees T3 or T4, so again, if I insert something down here anywhere, what we're going to see is that we're going to get a, if now we see we're going to get a, what we call as a right-right imbalance. I should have put the T in here. Detected at T. To fix this imbalance, what we'll do is we'll do a rotate left, or I guess I can just say a left rotation. on T. So again, what we're going to do is we're going to do a rotation like this. So when we see that, again, here we have an imbalance because we've gone too far down to the right. We're going to do a left rotation. And again, it's the node that comes out of balance. It's the way that, again, the side with the greater height, as we go down towards that size, that's where we declare what type of imbalance we have. So in this case, what's going to happen when we rotate left is what we'll have, if we have this is like 1, 2, 3, what we'll have is 2 will rotate up to the top. 1 will now be 2's left child. 3 will still be, again, so nothing really happens with 3. It just kind of gets pulled up a bit, but it doesn't, the link between 2 and 3 doesn't change at all. But then again, we've still got our, in terms of our subtrees, we still know that T1 should be to the left of it, all 3 of those nodes. We know that T2 should be in between 1 and 2. So T2 is going to be here. We know that T3 is in between 2 and 3, so it'll be here. And we know that T4 was greater than all those nodes. So the key thing here was that when we rotated 1 down, this, we saw that T2 was kind of adopted by T1 so 1's right child used to be 2, now it adopts T2 as its right child, and 2, which used to have its left child left arrow go down to T2, now goes down to the 1. But we see that the binary search tree property is maintained here in terms of the values of the nodes also being within their respective range based on their parents. Does this make sense? I guess I should have drawn this a little bit deeper, but we'll just assume that beforehand it was actually balanced. So again, here, if I again insert down here somewhere, what's going to happen is we would again get an imbalance on this top node, but in this case, we'd go right and then we'd go left to reach that imbalance. So in this case, it's going to be a right, then a left imbalance. And what that'll do is we're going to have to first do a rotate right, then we're going to have to do a rotate left. So I'll say that we have to do a right, left rotate to fix this. So what we're going to have first, when we want to do this rotation, we can still know that, again, T1, I guess if I've got my numbers here again, 1, 3, 2. We know that T1 has to be less than all the nodes, 1, 2, and 3. This has to be between 1 and 2 because we went right from 1 and left from 2. These have to be greater than 1 and greater than 2, but less than 3, so between 2 and 3. And these have to be greater than 3, just by where they're ordered in the binary search tree. Yeah, they're just arbitrary subtrees, and I'm just kind of generalize what the range of the elements in those trees have to be, so that we can show that after the rotation, all those elements would still fulfill that binary search tree property. Does that make sense? Yeah. So what we'll see here is when we do our first rotation, we're not going to change 1 at all. It's still going to go down to T1. Maybe I can do my trees in another color. So 1 is still going to go down to T1. We haven't actually done anything with 1 at this point. But now what we do is we see that this T3 here is, because 3 is now going to be 2's right child, 3 is going to adopt T3 as its left child. So again, what we're going to have here is we're going to actually have T3 and T4 like this. And at this point, T2 doesn't, oh, that should have been T2, sorry. And at this point, T2 doesn't change. So again, we've still got T1, which is less than all the nodes, so it's in the right place. T2 is again greater than 1 and less than 2, it's in the right place. T3 is less than 3 and greater than 2, it's greater than 2, less than 3, it's still in the right place. And T4 is greater than all of them. So we've still got all the elements in their associated subtrees are still left or right from these 3 nodes that are involved in the rotation. But we still haven't kind of fixed our order yet, or our balance yet. So we need to now, we finished the right rotate. Now we have to do this left rotate on, so this is the right rotate on 3. Now we're going to do the left rotate on 1. And what that's going to do is, again, now 2 is going to go up and be the root. It's going to go down to 1. Its right child's going to stay as 3. And in terms of our subtrees, again, nothing's going to happen between T1 and 1. What's going to happen is 1 is actually going to adopt 2's previous left child. 3, nothing's going to change with 3's children at this point. And again, if we think about how to make sure these are all ordered, again, all the elements in the subtree T1 have to be less than 1. They are. All the elements in subtree T2, we saw that right from the very beginning, they had to be greater than 1 and less than 2. They still are less than 1 and greater than, sorry, less than 2 and greater than 1. So those check out as well. The items in tree T3 have to be less than 3 and greater than 2. They're still greater than 2 and less than 3. So those check out as well. And in tree 4, they're just greater than all those nodes. So they're still greater than 3. So what we've done is we've now made it so this tree is balanced, but we've also made sure that this doesn't actually affect the ordering in our binary search tree, so we can still get those really efficient finds and insertions into the right slots as we continue to use this tree. Does this make sense? I'm seeing one yes and cool. So I did this in kind of this general form, just with these subtrees we don't even look at, because we're going to see that we don't even need to. So now when we're actually working with a real binary search tree like we are on the right, we're going to see that we don't really need to even think about any other nodes in the tree except for the kind of 3 that are involved in that rotation. And so although I guess the examples can be more complicated when you're working with this large tree that has a whole bunch of nodes, it doesn't actually matter what happens with those nodes, because none of these other subtrees are going to be affected. The only nodes that are going to be affected are the 3 that are involved in that rotation. I'm not sure if I'm still figuring out the last 2 assignments. I'm not sure if you'll actually do programming for an AVL tree or not. There's a couple different types of trees we're going to talk about over the next few weeks, and we're going to get into graphs. So I have to try and balance out what you're going to be doing in your assignments over these last few topics. So we'll see. You'll certainly do it in one form, whether or not it's like a written question or a programming question. But I'm not sure what you're going to be the programming and what you're going to be the written questions at this point. So I guess the question here, if we've got a binary search tree that again is a valid binary search tree in terms of it being a binary tree and a binary search tree, yeah. So we are doing red-black trees next. How many valid locations are there to insert a node into a binary search tree? So if we've got a valid binary search tree and we want to insert a node into it, how many different places are there that we can insert that element that will maintain the binary search tree property? What do you all think? So like, if I wanted to insert 30 into this tree, how many different places could I insert it so it would be in a valid location? Yeah, so in terms of the initial insertion, like I can't insert it over here because that would break the binary search tree property. It has to be a node, a 30 can't be to the left of 10 because 30 is greater than 10. Yeah, so what Josh is saying is there's only one thing. If I want to insert a 30, I know I'm going to have to go left from 38, right from 13, and right from 25, and I'll insert the 30 here. And that's the only place in this binary search tree that I can actually insert this element. So yeah, as Joshua was saying, there's one place to insert it. And then after that, once we've inserted in the one location, then we can determine whether or not there's an imbalance. We need to do some rotation. So one of the key things to note here is that there's always just one. In any binary search tree, there's just one place we can insert that node if we want to maintain that binary search tree property. Because again, we know that any node, for all nodes, all the children in its left subtree are going to be less than that key. All the nodes in its right subtree are going to be right from that key. So if we want to insert a 95, that means there's only one place we're going to insert it to maintain that binary search tree property. And after we do that insertion, then we can start thinking about doing the rotation to maintain that balance property. So again, if I'm inserting a 95, I know I want to go right from 38. I want to go right from 51. I want to go right from 84. I want to go right from 89. So it looks like I'm actually just going to insert it right in the very bottom corner because it's bigger than every element in this tree. And now from this point, I'd probably just go up from that point and calculate the balance factor of every node from my insertion up. So this is going to have a height of 0. This is going to have a height of 1, and its left side here is going to be -1, so that's still fine. This is going to have a height of 0, so if I compare these two, they're still within 1. That's great. This is now going to have a height of 2. This is going to have a height of 0. So we see, oh, these two, we've got a problem here. This is out of balance because its right subtree has a difference. The difference between the height of its left and right subtrees is greater than 1. And we're going to go up from this insertion and find the first place where we find this imbalance, which is going to be here. And again, we're going to see it's a right imbalance because we inserted that node down to the right. So we're going to see that we have a right imbalance at node 51. Oh, is there some noise? So I think my volume is really low, so I might not have been able to hear if other people were talking. I'll turn my volume up. There we go. Sorry about that. So if we've got a right imbalance at node 51, how can we fix that? What type of rotation can we do to fix that? Yes, we can do a left rotate here on the 51. So what'll be the result of that is, I hope I can actually draw this, have enough space for this whole tree. So none of these nodes are going to be affected in any way. What we're going to see is we are going to have something happening here. So what's going to happen is 84 is going to rotate up to be the new root of that subtree. 51 is going to rotate down, so it's going to be 84's left child. the 89 is going to rotate up. And what's going to happen in terms of adoption? What other nodes might be affected by this? So I've kind of now, I've done the work on the 3 main nodes that are affected by the rotate. But what happens with the other nodes around these, the other subtrees that associated with these? So what's going to happen to 40? So 66, so this is going to be the one that's adopted by the original root, the 51. So I guess the adopted node here is going to be, I can do that in blue, is going to be the 66. And other than that, nothing else changes. 40 is still going to be the right of 51, and 95 is still going to be the right of 89. So the only other thing that's ever affected is the node in a rotate left, the node to the left of the node that's going to be rotating up to be the new parent of that subtree, it is going to be inherited by the previous root of that subtree. But this is the only node that changes. I'll highlight in blue. The only node that changes is this node here. All these other ones aren't going to change at all. And nothing on this side of the tree is going to change at all either. So it is quite a localized restructuring of the tree. And now we can go up and check all of our heights and make sure that none of them differ by more than 1, which we see that they will be fine now. 0 and 0 and 0 and 1 and 1, 2, 0, 0, 1, 3. So yeah, these are off by 1, but it's still not enough to be an imbalance. Or it's not enough to be an imbalance that requires a rotate to fix, because we're allowed to be, we're allowed to have a difference of 1. Any questions about this? Maybe I'll do a quick. So in terms of, I guess, this poll can, I guess, in terms of your understanding, it can ask a few things. One, do you understand kind of where to insert or how to do removal from a BSC? And then also, once you've completed that step, are you confident in being able to identify if there's an imbalance and fix that imbalance? It gets a little bit more difficult, but again, it is quite local. Again, you do an insertion, you can, because you can just break it down into small steps. And again, the recursive natures of trees makes it quite easy, because again, you can just look at each subtree as its own thing. It's not like you have to kind of do crazy while loops starting from the root and do all this stuff. Recursion makes working with trees, because you can just kind of think of each as its own separate subproblem. So looks like almost half of you are quite confident. Again, then the next highest are kind of saying it makes sense as we go through it, but you're not sure you can do it on your own. There are a few of you that are starting to get there, and a few that it doesn't make sense yet. So I guess I can say now that the plan for Friday is we'll see how far we get through today. We might kind of be able to wrap this up on Friday. The quiz for Friday, in terms of the pre-lecture quiz, is going to be not a quiz on new material. It's more going to be a quiz on exam format. And I just want to see if people are comfortable doing different types of formats. So one thing I've explored, which I think might be a good way to do it, is actually having you be able to upload and attach a file like you would an assignment. So if you've got work to show that you did on paper, you could take a photo of it and just upload it into the assignment section. or if you're more comfortable kind of even doing something with something like this, where you're able to kind of annotate on with a pen on a tablet, and you can export that as a PDF and upload it that way. But I just want to make sure everyone has the resources and is comfortable doing that, because again, for the course, in the course outline, I didn't specify that you needed to be able to upload files very, very quickly. I mean, it's one thing to get you to try to do it over a week when you've got an assignment, but it's something else to ask you to do it during an exam. So it's something that I have some ideas about, but I'm gonna, instead of introducing new material, we'll probably have the cutoff for the exam as AVL trees. And I'll ask some questions about just whether or not people feel comfortable doing different types of exam formats, because I do think if everyone has the resources to be able to do something like that, I think it probably is better and more fair than because I know that some people had issues when they were solving the problems on paper for the first midterm, but just couldn't translate that into the format that the tests and quizzes were done on. So this one's going to be a two-step rotation. So here, again, we're going to insert a 35, and we now know that there's only one place we can insert it. We're going to start at 38, which is the root. We only have access to the root in an implementation of this. So starting from the root, we can say, okay, do I go left or right from here? I'm going to go left from 38. I'm going to go right from 13. I'm going to go right from 25. So this is where we're going to insert that 35. And so now, again, we can just work our way up from here. We've got this one. If we compare all of the heights of the nodes, we see we've got an imbalance here because we now go right from here, and again, this one's right subtree, or sorry, we've got an imbalance on 38 because again, this tree is height 2 and this is 0. So again, from here we go, we go left and then right to go to the source of this imbalance. So we've got here is we've got a left-right imbalance on node 38. And how do we fix that left-right imbalance? Yes, we're going to rotate left here and then right here. So we can think about the first one when we rotate left. We know the rotate left is just going to kind of be on these 3 nodes. And what that's going to get us is it's not going to affect the 38 in any way. It's not going to affect the 51 in any way. It's going to now have 25 be the new root of this subtree, which is going to go, 13 is going to go down here, and nothing's going to change between 13 and 10. And 25's right child is going to maintain 35. And we didn't need to do any adopting of 25's children because there was no node here. So there's nothing to adopt for 13 to adopt. So this is quite a simple left rotation. But now we see we still got something out of balance. We've still got that again, the heights of these 2 subtrees here, this is height 2, this is height 0. So we still need to do that right rotate on the root. So when we do that, we're going to see that 25 is going to become the new root. The right child is going to be 38. There's nothing changing between the 38 and 51. The left child of 25 is not going to change. Either is its left child. But what happens to the 35, I guess, is the question. Yeah, so it's going to be, or not 51, yeah. So it's going to be adopted by the previous root, the 38, as it gets rotated down. And so one thing, Yuming, to help make sure you're right in this is if we had done it down here, which the thing that we would have seen why that doesn't work is because now if we find that 35, we'd go right from 35 and left from 38. So we would never find that 35 if it was left at 51 because it has to be the left side of the 38 in terms of our binary search tree property. And now we see after this double rotate, we've got a balanced tree again. And an ordered tree in terms of the binary search tree property. Any questions about this? So I'm hoping by the time we finish this worksheet, what you'll start seeing is, again, it's once you see the pattern here, it's I guess the challenge is seeing the pattern, but once you see the pattern, there's these 4 different rotations that can occur. The rotation process becomes fairly straightforward in terms of the fact that none of these rotations are very complicated. There is really just like a left rotation and a left-right rotation, and then the other 2 rotations are just mirrors of that. And again, it's the same thing with the imbalances. We've got either in terms of our imbalances, like we've got like a left-left or a left-right imbalance, and then the right-right and the right-left are just kind of mirrors of those other 2 imbalances. So again, the way we fix each one of these imbalances with our rotations, the rotations themselves, the main thing to think about is kind of the fact that sometimes we need to adopt that child. That's kind of the only, I guess, really tricky part. But other than that, the rotation itself is just kind of, it's always just doing this shift of these 3 nodes where, again, one becomes the root, the other one rotates over, and the other one rotates up. So any questions before we move on? Okay, so what I want to do next, we'll see, we might get to 1 removal today, but maybe not, is do a whole bunch of insertions one after another and think about how when we do this, how to determine when we need to rotate and when we don't. So what I'll do, I might actually go down a font size here. So what I'll do is we'll say first we'll insert 71. Oh. And obviously there's just 1 node, there's no imbalance there. So what we'll do is we'll then insert the next one, the 13. So we've got 71 as our root, and then we're going to insert 13 on the left side of it because 13 is less than 71. So we've done the first 2. Now we'll insert a 65. And where's the 65 going to go? Yeah, so it's going to go left to 13. But then again, because 65 is greater than 13, it's going to go to the right here. So again, we're always just comparing the values here to get that binary search tree property. Because again, we know that everything in 13's right subtree should be values greater than 13. Everything on its left subtree should be values less than that value. Yeah, cool. So now Leo's saying it's imbalanced. What type of imbalance do we have and on what node? Yeah, so now from 17, we've got a left-right imbalance here. So to fix that, what we're going to need to do is do a left rotate on 13, followed by a right rotate on 71. So to do that, what we're going to get is we will first get that 71 is still the root. Then when we rotate left here, we're going to have 65, then 13. Because again, 65 rotated to be up of the parent with that left rotate. So we've done the first rotation. Now we need to do the second rotation. And maybe I'll just kind of pull this down here. And when we do that, what we're going to get is 65 is going to rotate up to be the root. 75 is going to rotate over, or 71, sorry. And the 13 is going to rotate up a bit. And since there's 3 nodes, we don't need to think about adopting any children or anything like that. Any questions so far? So if we've got a right imbalance, we know that we're going to do a left rotate. If we've got a right-left imbalance, we'll do a right rotate followed by a left rotate. If we've got a left-left imbalance, we'll do a right rotate. And if we've got a left-right imbalance, we will do a left, then a right rotate. Oops. So there's our little cheat sheet right there. So we've now finished the insertion of the 65. It took a while because we needed to do a double rotate there. We finished the 65. Now we're going to insert a 22. So when we insert the 22, where is it going to go? Yeah, you got it, Omar. So again, it would obviously go, it's less than 65, so it's going to go left first. Then it's right of 13, so it's going to go left of 13. Do we have an imbalance here? Nope. Yeah, it's okay for now. So we'll insert the 49. Where's the 49 going to go? Yeah, so it's going to go right of 22. Do we have an imbalance now? Yeah, so we've got a right imbalance on node 13, which Owen is saying is a rotate left. So what's going to happen there is we're not going to affect the root. It's still going to be 65. We're not going to affect the 71. What's going to happen is 22 is going to rotate up to be the new child of this subtree. 49 is still going to be its right child, and its left child is going to, or the 13 is going to rotate down. So the thing is, typically you go up from the inserted node and find the first imbalance, and that will fix it, as opposed to starting at the root and going down. Because what would have happened if sometimes at the root and going down, you'll do some rotations which will cause other rotations to have to occur as well. Whereas typically we don't have to do, we can minimize the number of rotations we do if we just start at the bottom and go up and make any rotations we need along the way. Sometimes we'll see this does cause a chain reaction, but typically it results in the minimum number of rotations necessary. So now again, we've successfully inserted the 49 and we've rebalanced. So we've got 2 left to insert. We're now going to insert the 37. Where's the 37 going to go? So I think for this, we can always just kind of do this really slowly. We know it's going to go left of 65. What way is it going to go when it sees 22? Yeah, you do, Leo. You always start at the bottom and go up from there. So we started here and we found that the first one was the 13. You're correct in that assumption. So Omar is saying to wait. What do you got for us now, Omar? Yeah, so again, when we insert the 37, we're going to go left from 65. Then we're going to go right from 22. Then we're going to get this 49 here, and we're going to go, oh, now I can go left from this. What do we think? Is this going to cause an imbalance? And on which node, if so? So for people that are saying there's an imbalance, on which node is it causing the imbalance on? So if we think about 22, we know that its children's heights are 0 and 1, but the 0 and 1, that's actually okay. Although they are imbalanced, they're not imbalanced by greater than 1, so it's actually okay there. But if we keep going up the tree, we see this is height 0, this is height 2. So we actually see that it's this node here that has an imbalance, because the difference between the height of its children differs by more than 1. Yeah, so we're going to start here. We're going to say it's actually a left, right from here. Yeah, so it's always, you can go up and you can just say, what are the differences in the height of my children? Is the difference in those heights greater than 1? So how do we fix this? Left, right rotate on 65. So it's going to be a left, right rotate on 65. So we can start with the left. The left rotate is going to keep us, 65 is going to stay as the root. 71 is going to be its right child. But then now we're going to rotate the 49 up here because we did a left rotate on the 22. 22 is now going to be its child. 49. So now how do I finish off this tree? What's going to happen with the remaining nodes here? Do we do anything special with the 13? Nope, nothing special with the 13. What about the 37? Yeah, so you're saying the 22 adopts 37. So yeah, again, if 49 is rotating up, then we're going to actually have its left child on a rotate left is going to be adopted by the parent, the 22. So what we'll see here is that the 22 now gets that 37. Do I have all the elements here? Am I missing anything? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, cool. So we've done the first half of this rotate. Now we need to do the second, which is the rotate right. So to do that, what we'll have is we will rotate the 49 up to be the root. Oh, that's gross. Oops. Um, 65 will be its right child. 22 will be its left child. Nothing happens with the nodes below 22 here. And the 71 just goes down. We didn't need to do any adoption because there was no node down here. If there was a node in this area that I've circled, we would have had to do an adoption, but there wasn't. So, and now we've successfully inserted the 37 and we've rebalanced everything. So the last thing we have to do is the insertion of 45. So again, we're going to have this same basic tree here. And where is the 45 going to go? Yeah, right at 37. And we actually, I don't think we have an imbalance here. Again, if you think about all of our heights, and if they differ, we've got a 0, we've got a 1, we've got a 0, we've got a 0, a 1, a 2, and this is a 3. So again, none of them differ by more than 1. So I think we're actually all balanced here. So that last one was actually an okay insertion. So I think we're now done doing all those insertions. So again, I think we saw, I guess we didn't actually see all the different rotations here, but we certainly saw like a bunch of lefts and rights different rotations and multi-step rotations. And again, the idea here is that you just insert as you would in a regular binary search tree, and then go up from that insertion, see if there's any imbalance, and if so, just apply one of those 4 rotates. And I kind of did our little rotation key over here on the right, where this is kind of the only 4 imbalances we'll ever see, and based on which one we see, we just do the associated rotation. Any questions before we call it? So yeah, on Friday, we'll do some removal. We'll see it's not that much different. There's the 4 different removal cases we need to think about when we're removing from a binary search tree. And then after we've done that removal, we just do the same thing. We look for an imbalance and we apply the associated rotation. So I'm working on a survey that I'll post in place of your quiz. And it's more just seeing if you're comfortable with different types of exams, because I want to make sure I'd like to create an exam that I think is better suited to an online exam, but I just want to make sure it puts everyone, it doesn't put anyone in a position where they're not actually able to complete the exam. So I want to make sure it's still fair for everyone. So that'll be the quiz. Then I think in the quiz, I'll also ask you about maybe if we can spend some time doing some sort of review on Friday, what topic you'd most like that review to be about. So what topic you're mostly feeling like you haven't had enough practice with. So that's what the survey will be about. So on Friday, we'll finish off the removal for AVL trees, and then maybe do a little bit of review on a different topic. And then the exam will be, again, in a week from today. So there is no lecture tomorrow because of reading week. There's no labs this week, but we will have a regular lecture on Friday.